My name is Ben Jenkins. I work as a senior data scientist for Sumer Sports. I'm also a PhD student at Florida Atlantic University. I'm excited to share our work applying causal inference techniques. Okay, yeah.
Go for it.
Okay, cool. So I'm excited to share our work applying causal inference techniques to measure the impact of offensive linemen on pass plays. Based on our knowledge, this is the first time that publicly that causal inference techniques have been directly applied to offensive line, and one of the few times causal inference has been applied to NFL tracking data. So estimating player performance is fundamentally a causal problem, yet it's often treated as a prediction problem. What I mean by a prediction problem is they typically train a machine learning model to predict some expected outcome or conditional mean, and then they attribute player performance to a residual value, which is the difference between the actual value and the predicted value. So current metrics such as rush yards over expected, you commonly see this in football games, they are useful, but they solely rely on correlation-based techniques to isolate the impact of individual players. Our methodology attempts to go one step further, which is not to just learn the historical patterns in the data, which is much more simpler. We're trying to identify the underlying cause and effect of players' actions. Causal inference is a statistical approach used to determine the effect of an action on a given outcome. And so, for example, here we're trying to identify how do offensive lineman actions, their movements on the field, impact completion probability. Causal inference is widely used across a wide variety of fields, including leading tech companies such as Google, Amazon, and Netflix. I previously worked at Paramount Plus as a machine learning engineer, and we use causal inference techniques to better understand our customers and identify ways we can maximize user engagement. Our methodology, which is CLIP, which stands for Causal Impact of Offensive Linemen on Pass Plays, provides a causal estimate of how pressures allowed by offensive linemen directly affect pass probability. This provides teams with actionable metrics that directly link player actions to game outcomes. So here's an example footage of rush yards over expected, and so this is a machine learning model that predicts at handoff how many yards a running back's expected to get. So you can see here Damian Harris is expected to gain 4 yards. He actually runs 26 yards, right? And so they attribute that residual value for 22 yards. Now I'm going to briefly talk about the difference between machine learning and causal inference. So with machine learning, the goal is to predict what will happen or what's likely to happen given the historical data set. And its key strength is it excels at pattern recognition as well as prediction tasks. Causal inference seeks to answer why and how something happens. And so the key strength with this is it provides insights into causality and decision-making impacts. So the specific model we use is called a doubly robust estimator. It allows us to estimate the causal effect in observational data. How it works is there's two components. The first is the outcome model, which predicts the probability of a completed pass based on features X and whether pressure was allowed. Next, there's a propensity score model, and that estimates the likelihood that a lineman allows pressure based on features X. It's termed doubly robust because it only requires one of the two models to be correctly specified in order to identify the causal effect. We are specifically interested in estimating the conditional average treatment effect, or the CATE, for each player on a given play, and that's the expected completion percentage on the play given features XI, given pressure occurred, minus the expected completion percentage on the play given features XI, given pressure did not occur. Two of the key advantages to this approach is it's robust to model misspecification, and it helps reduce bias from confounding variables. So here's an example of a failed block play, and so this is Tua Tagovailoa completes a pass to Mike Gesicki. You can see here that two of the offensive linemen fail their assignment and allow the quarterback to be pressured. And so everybody here who's a football fan knows pressure is bad, but the question is how did this pressure on this play directly affect completion percentage? And more importantly, how well did each offensive lineman perform, and how did their actions directly affect the outcome of the play? And using our methodology, we can start to answer these important questions. So we can see here on the bottom left figure is the actual locations on the field. So this is the lineman's XY coordinates, and you can see each color shading representing their performance. In green and red, green means they're performing positively, red means they're performing negatively. And what you can see, our model was able to correctly identify the two linemen in red that were contributing poorly and actually decreasing the chance of a successful play. In the middle figure, we can actually see it over time now. So the x-axis is every 1/10 of a second, and the y-axis is just their each individual values. And we can see some values remain consistent and some values change. And so you can see it's changing due to the changes in their features and how well they're performing. And so this kind of provides more granular level insights that we can provide. Lastly, we can look at the clip values for the entire offensive line, and we can see the values start at 0.10 to 0.15. And so we can say that 10 to 15% of the completion on this play can be directly attributed to the offensive line. And this is something that other metrics that only rely on correlation cannot state. Now we'll look at another example of great pass protection. So Jimmy Garoppolo in 10 completes a pass to Deebo Samuel. And what I want you to take note of in the beginning is the quarterback has plenty of space to operate. So he's able to complete this pass. And so the question is, how much credit of this play should be given to the offensive line or the wide receiver or the running back? And so we're going to start showing this next. So the bottom left is the same plot from before, which shows their player locations on the field. It's now shaded from purple to green because everybody actually contributed positively and there's no pressure allowed on the play. And so we can see the values in the middle change every 1/10 of a second. So some of the best performers on this play were Daniel Brunskill, and one of the worst players was Trent Williams, but he's still positive. Lastly, if we compute their values for the entire offensive line, their values are 0.6 to 0.8, meaning 60 to 80% of this play can be attributed to the offensive line itself, which kind of highlights the benefit of having a strong offensive line. So we ran a variety of validation tests to ensure that our methodology was working correctly and superior to other techniques. And we found our causal model was significantly better at being able to identify the top offensive lineman, as indicated by All-Pro and Pro Bowl honors. So these are players that are recognized as being the best of the best. And we see in the dark shading in green that our methodology is much better at able to identify the top players. We also found our methodology is significantly better in terms of ranking players based on salary. So it's much more consistent in terms of that. So now instead of looking at individual players, we can aggregate it in a sample data set from the 2023 NFL Big Data Bowl. And what we can see is there's a strong positive correlation here between our methodology and independent rankings. So this is comparing Pro Football Focus results with our rankings. And what we find is that there are some differences. We were only given the first 8 weeks of the 2021 NFL season, and Pro Football Focus had the entire data set to work with. We also found, We also found that our causal model is strongly correlated with completion percentage on an individual play, meaning that teams tend to have better offensive lines, tend to complete more of their passes, as well as they tend to win more games over the season. So this highlights the importance of having a very good offensive line. So we ran a variety of robustness and validation checks. So when you're working with causal inference, you need to be able to run tests in order to ensure that your methodology is sound and that it meets see how sensitive it is to the various assumptions you made. And so one of the key things we looked at was covariate balance. And so we found that the standardized mean differences was less than 0.1 after a weighting, which is ideal. We ran placebo tests, and so what we did there is we changed the treatment effect with the placebo, and what we found was that this helped confirm that treatment effect is not due to chance because the treatment effect went to 0 when we changed it with a placebo variable. If you've actually identified the causal effect in the data, then your estimate should remain consistent across random subsets of the data. And so we did some sample validation. This helped confirm that our Kate values remain consistent. We ran sensitivity analyses, and so what we did here is we added unobserved confounding variables and measured how robust our estimates were, and we found that it remained very robust with less than a 3% variation in the Kate values across various simulations. Lastly, since we're interested in the propensity scores and in predicting probabilities, we made sure that our models were well calibrated, as well as we looked at AUC curves. So in conclusion, many previous adopted metrics, which you see on TV and are widely publicized, such as rush yards over expected or completion percentage over expected, are useful, and they've shown to provide value. However, they're limited by their reliance on methods that cannot measure cause and effect. Our methodology attempts to go one step further, which is to identify the cause and effect in the data. Our model allows NFL teams to make more informed decisions, enhancing player evaluation and game planning. We think this is a strong framework that can be applied to measure other positions, as well as other professional sports, such as basketball, soccer, or hockey. Lastly, we hope that this begins the transition from reliance on prediction and correlation in sports analytics towards a focus on cause and effect. Thank you for your time. I'm happy to answer any questions.
Great job. Would it be fair to say, overall, a summary of the project is you're analyzing the propensity to allow a pressure, combining that with the severity, the impact on completion percentage, given the pressure is allowed?
Yes, in simple terms. Yeah.
So, and you're using pressure allowed as an input to the model?
No, they're two separate models. So one is, I can go back, let's see if I can go back. So there's two models in here. The first model is so let me see. Yeah, first model is the outcome model, and so that's predicting what's the probability of a completed pass based on the offensive lineman features and relative players' features, whether pressure was allowed. And the propensity score model then estimates whether the lineman allowed pressure based on the features. And what the propensity score model attempts to do is using a technique called inverse propensity weighting that's trying to create a more balanced data set where we can actually measure the differences between in the outcome of a play.
Okay, so the features are doing all the heavy lifting.
Correct.
So I don't think you have a slide on it, but in the paper, the features were, I don't know, it was confusing to me. Maybe you can convince me. It seemed like there was variance of the X locations of the lineman, variance of the Y locations of the lineman, maximum offensive lineman acceleration.
Yeah. So it's with the tracking data, right, from the big datable. So I include the locations of all the offensive linemen as well as all the teammates and as well as the opposing players. And so I kind of had the model figure out what was important there, but I tried to account for the proximity of the offensive line to the quarterback, the proximity to the nearest defensive players, as well as like the proximity to the nearby teammates as well. Yeah.
And so I guess indirectly then you are accounting for at least the defenders in the equation.
Correct, I account for the defenders, yes. Their XY, their speed, their distance to the quarterback, which can obviously affect pressure as well as completion percentage. And we model this every 1/10 of a second so we can see these fluctuations as the play progresses.
Okay, thank you.
Yeah, thank you.
Ben, I think you did a really good job. I want to look through the lens of a coach.
Yeah.
So if a coach were to come up to you, and let's say, well, I was going to say a college coach
Sure.
and a high school coach, but high school coach, you can't really find data. But let's say if you're looking through the lens of a college coach and they say that, Ben, that this is really good, do you think that this is something similar with the college game, especially when it comes to the P4 and the G5 schools, as opposed to what you were able to come up with your research with the NFL?
Yeah, I think you could apply this to college and P4 data. The nice thing is we have computer vision in the college level, so we're able to get the actual tracking data. And so we can apply this to the college data as well, and so analyze the linemen's. An important consideration there is to probably make greater account for the competition differences, because quality of competition is going to be important in college more than NFL. But yes, we could apply that to college and provide some insights there. Yeah, thank you.
So first, let me say, you had me at causal over correlation.
Yeah.
That's great. Love it. My question is actually related to Brian's. I also had a little bit of trouble understanding what the features were, but I think
Sure.
I get it now. This is, I think, maybe just a notational thing. So TI, is this a binary variable, or is that the color that you showed in the
Perfect.
plot? Yeah.
Sure, great question. Yeah, so if I go to, you mean like this plot right here?
Yeah,
So
exactly.
T is actually a binary variable, whether pressure was allowed, but we model it not in binary, we model it with probabilities from 0 to 1, and so this allows to see the shading differences. And so it is binary, but we model it with a probabilistic model that allows us to estimate from 0 to 1.
I see. Great.
Yeah.
Great.
Yeah.
Thank you.
Yeah,
Yeah,
thank you.
really nice time. Thanks.
Thank you.